Okay, so let's carry on and start reviewing semi-supervised learning. Semi-supervised learning. And in particular, graph semi-supervised learning. Because graph theory-based semi-supervised learning is much more natural and successful among all different algorithms. So GSSL methods, you can label you want to infer the label. So it's a label inference problem. And I will talk about graph regularization, and then I will talk about graph embedding, because there are different topics in the literature. So advantages of graph semi-supervised learning over semi-supervised learning is that your data set is more natural to the graph, World Wide Web, citation networks, social networks, political networks, security, and all those things are very natural. So convexity, if you have a symmetric graph, you can use convex optimization techniques, which is more feasible and tractable, let's say, and scalability matters because the time complexity is linear to the total number of samples. On the other hand, I want to talk about your problem setting is either transductive or inductive. So it's so mouthful, Transductive, people mean different things at different contexts. Transductive it means that only labels of unlabeled nodes in the training data set need to be inferred. So only labels of unlabeled nodes. But inductive, the trained model can predict the label of any unseen node. And transductive inference is reasoning from observed specific training cases to specific test cases. Induction is reasoning from observed training cases to general rules. Of course, the first time, who was that? Vladimir Vapnik used it for support vector machine, and he said, for example, that first we should solve some simple problems rather than the whole problem, and so it's a bit of philosophy, and let's talk about. Of course, a majority of graph-based inference approaches are transductive. Now I want to start and say that all of these articles are just different ways of evaluations of these terms that I will talk. First of all of them use the objective of supervised loss. So this is the supervised loss. You cannot change this very much in your article. But the unsupervised loss, it could be F. So this is the unsupervised loss. And of course, you can write for regularization term as well, f and d. But for graph Laplacian, we merge these two. For graph semi-supervised learning, we merge these two, and it becomes so it's just one regularization term plus your objective for supervised learning, this is the traditional learning, and L of f. But this one is new. So this is because you have unlabeled data. So you can write this as, for example, this one could be written as xi and yi over all your labeled data, I and yi. And this term is just sum over all data, labeled and unlabeled. So it's regularization objective function of f of xi. So the first attempt to deal with semi-supervised learning, not the first one, but the first major attempt is label propagation. It's very related to random walk theory, LP. So Z.Ghahramani in 2002, this Iranian-American scientist wrote a very interesting paper. And so in step 1 of his algorithm, all nodes propagate labels for one step, so ty. And t is the probability to jump from node j to I. So let's write it, probability from jumping from node j to I. And it is natural to define like this. K from 1 to label and unlabeled. So all of your data. And so you can decompose your y into y of labeled and y of unlabeled. So your your y is labeled plus unlabeled times c. C is a number of classes, 2 for example. And so you can also decompose t into t of labeled, t of labeled, unlabeled, t of unlabeled, labeled, t of unlabeled, unlabeled. So if you write this, of course, your weights is just the traditional. d from 1 to d squared sigma 2. So you can rewrite your y as t unlabeled, y of labeled, and so it's an iteration. So in this iterative formula, if you just do it recurrently, you will notice that you can write this as limit of tnu y0 plus I from 1 to n tu I minus 1 TULYL, and we just need to say, it is proved in this paper in 2002 that this goes to 0. And so if that goes to 0, it is easy to show that this problem has a fixed point of y of u is equal to I minus TUU inverse TUL YL. Of course, in practice, they don't invert this matrix or any large-scale matrix, and it is not scalable. That's why they use different methods, different iterative methods, such as conjugate gradient and etc. So, of course, this is a really interesting formulation, but it has some limitations. And of course, the Zhu in 2004 has entered the multi-class version of that, which is his article, which is named by local and global consistency. Let's say LGC. In that paper, his iterative process that I've just mentioned, alpha is a hyperparameter, and is now like this. Of course, S is the AD, and it has a closed form solution. Again, it has a closed form solution. 1 minus alpha y is 0. And it turns out that it's very interesting that this LGC method actually minimizes this problem. Wij 1 over dii f of x I minus djj f of xj. So it's actually minimizes, so everybody are talking about the same thing. They just reach it in from a different direction. F of xi minus yi squared. And this is the influence of high degree nodes. So high degree nodes is regularized. So we consider it because we want to say that high degree nodes are regularized. A variant of LGC is P Laplacian. So instead of 2, we write P. And so this is the P Laplacian approach. Another similar approach is the directed regularization. Now for directed or graphs, such as citation networks are directed graphs, so that's why this method could be useful for them. J to I, Pj, and probability of a J and I, of course, which is defined by Wij d plus of I, Wij sum over Wij. And the cost function is, your objective function. You just want to minimize this. So it's very close to the previous objective function, but now we have some weighted approach, something like f of x I minus 1 over djj f of xj squared plus mu I from 1 to number of labeled data, and this is the traditional part of that. So it's like the previous approach, but you have this extra weight as well. And now I would like to start manifold regularization, which is quite elegant and fantastic method in semi-supervised learning. I don't want to say that it is one of the best papers, but it is really interesting. It is. I really like this paper. So manifold regularization. So I can say that it is one of the best papers written by Belkin and also his friends Nyogi and Sindvani, I think. So it combines many different aspects, such as spectral graph theory, such as manifold learning. So it searches for low-dimensional representation, but with a smooth constraint. So this article, which is about 35 pages, I will describe it, but let's define induced NOR, which is 1 over n number of labeled, number of unlabeled, y hat transpose L y hat. And plus y hat is now f of x1, f of x number of labeled plus number of unlabeled. So in 2010, we also have Z.Ghahramani discriminative semi-supervised feature selection via manifold regularization. So the idea of manifold regularization, I mean, the original work is that this is the example of original work. So you have a set of points, data points, and you want to classify this problem, which is a semi-supervised learning problem because you have both labeled and unlabeled data. For example, this is one label, so it's just two labeled problem, this one and that one. So you can separate them by, you may say this one is okay, but the better separation is that if you respect the density of your data, so the better separation is this. You have separated them. And so you want to limit the change of labeling function. You want to limit the change. Plus even the derivative. You want to limit the derivative. and so if you call this